TRAX, Tracking in Complex Sensor Systems.
Today, my topic of the presentation is proximity-based particle filtering. The contribution of this work has been published on the International Conference on Information Fusion in Washington, D.C., 2015.
Hello, my name is Yuxin Zhao. I'm an early-stage researcher working on the TRAX project at Ericsson in Linköping, Sweden.
First, I would like to introduce an outline of the presentation. At the beginning of the presentation, a system overview of the problem to be solved will be introduced. Then, I will give a brief summary of the proposed proximity-based particle filtering algorithm, including some prerequisites. The models that are going to be used in the algorithm will be described in detail in the following section. Thereafter, the particle filtering algorithm for both periodic received signal strengths and event-triggered proximity reports are introduced, followed by some results comparison. Finally, I will conclude the presentation and give the outlook of our future work. Over the past few years, indoor positioning use wireless sensor networks has received considerable attention due to the ever-increasing demand on location-based services that are widely used in a lot of applications. Motivated by this, we propose an event-triggered proximity report-based particle filtering algorithm. Unlike the conventional positioning based on periodic received signal strengths, the model complexity appears as a hard thresholding when converting an RSS measurement into a proximity report. The proximity report will be triggered only when the mobile crosses a border, as shown by the cross marker in the figure. A proximity report obtained in this way reveals whether or not the reporting device is in the coverage area of a reference network node. From this, we can see that by utilizing event-triggered reporting scheme, we can save a lot of signaling overhead. In this work, we assume an optimized threshold has already been obtained. Then the signaling procedure to perform the positioning algorithm is illustrated in this figure. On the network side, a computation entity will configure the mobile device of the optimal threshold. Then the mobile device measures the RSS of the signal which is sent from the reference network node. The RSS values are then converted to proximity reports, which are going to be sent to the computation entity for position estimation. Before we perform the particle filtering algorithm, some prerequisites are needed. First, we have to obtain the deployment information of the indoor area, which we are interested in. For instance, a map of the building, the locations of the network nodes, and so on. Also, we need to train a proper propagation model and obtain an optimized RSS threshold. Then, in the next step, the motion model has to be assumed, and the measurement model for both RSS and proximity reports need to be defined. Finally, with all this information, the particle filtering algorithm for position estimation can be performed. So in the next slide, detailed descriptions of all these models will be introduced. First of all, the propagation model used in this work is a classical linear log distance model, which represents the one-dimensional relationship between the distance and the received signal strength. In what follows, we consider state space models that are linear in the state dynamics and non-linear in the observations. For instance, we use the following conventional motion model to relate position and velocity indoors, where xk is the underlying state vector at time instance k. Two observation models are considered in the sequel. We start with the RSS measurement model and followed by a proximity model. It's noted that in the RSS measurement model, the noise factor is additive and thus linear to the measurement vector. However, in the proximity model, nonlinear noise factor is introduced by the nonlinearity of the function fx. Solving filter problems with this non-linearity will be the main focus of the remainder of this work. The particle filtering algorithm is introduced as follows. We start with generating particle samples from a pre-selected prior distribution. The weight of each sample is equally set to 1 over n, where n is the total number of particle samples. Then, we use the sequential importance sampling algorithm to propagate particle samples and perform width update. The estimate state vector is obtained by taking the weighted sum of all particle samples. Also, resampling is performed whenever necessary to prevent high concentration of probability mass at a few particles. In what follows, we will show some results based on the proposed performance of the proposed algorithm under real circumstances. We also provide results with real measurement data which are collected along the 52 predefined tracks. Similar performance is still achieved for proximity-based positioning compared with RSS-based positioning. It's noted that in real circumstances, due to the complex indoor propagation conditions, the estimation of positions may be difficult. For instance, near the lower corridor on the figure, the user may also hear strong signals from beacon 8 and 10, so that the user may have been fooled that is close to beacon 8 and 10. This may also explain why the estimated positions for those points are very close to beacon 8 and 10. The selection of RSS threshold can be critical in determining positioning accuracy. The comparison between various RSS thresholds is shown in this slide. The lowest root mean square error is achieved at -82 dBm. This is reasonable since with a high threshold, for example -70 dBm, the receiver may not within any beacon's coverage, while a low threshold may lead to the case that the receiver is within all beacons' coverage. In both cases, little information can be obtained, and the positioning accuracy may degrade due to the loss of information. The CDF of estimation errors at each position is illustrated then. We can see that for simulated data, a median estimation error of around 2 meters can be achieved. For real measurement data, median errors of 3 and 4 meters are obtained for RSS and proximity-based algorithm, respectively. As we mentioned before, the main advantage of event-triggered proximity reports is to save signaling overhead. So here we summarize how much data we can save. By sending the event-triggered reports instead of periodic reports, we can reduce the total number of report vectors by around 10 times. Further, by using 1 bit proximity instead of 6 bits quantized RSS value, the total number of bits can be reduced by around 40 times. From above results, we can conclude that the positioning performance of the proposed algorithm is comparable with that of the conventional one using RSS measurements. We have further demonstrated that the selection of RSS threshold and the spatial distribution of beacons are essential in determining positioning accuracy. Such an event-triggered proximity-based particle filtering algorithm is beneficial in different aspects, among which the signal overhead can be significantly reduced by sending binary proximity reports less frequently instead of sending quantized RSS values periodically. In our future work, we will continue to look into Bayesian smoothing methods and other proposal distributions of particles. Also, we would like to derive some fundamental lower bounds. For instance, posterior and parametric Cramér bound. Further, more complex and realistic propagation models, such as Gaussian process regression model, may be studied. Last but not least, the spatial correlation between measurements from different reference network nodes may be interesting to look into. That's coming to the end of the presentation. Thanks a lot for your listening.
For more information about TRAX, please visit our site at trax.u20.nl.